Not long ago, astronomers finally confirmed that our galaxy is very likely located near the center of a giant cosmic void. April 2026, a new paper released on the Arxiv Astrophysics Repository showed that the Milky Way may lie inside a giant void with a diameter of 2 billion light-years. This could directly resolve the long-standing Hubble constant crisis and the problem of dark energy. Many people imagine that galaxies in the universe should be distributed fairly evenly, making it difficult for vast blank regions to appear. In reality, however, the universe contains a large number of cosmic voids. A void is not truly empty. It is simply a region where the density of matter is far lower than the cosmic average. In terms of the universe's total volume, voids occupy more than 70% of space. One could even say that most of the universe is actually void. So how exactly did these voids form? We know that after the Big Bang, matter was released from the singularity, and the universe immediately entered a phase of inflation. Expansion was far stronger than gravity, pushing matter farther and farther apart. As inflation weakened, matter began to gather again under the influence of gravity, possibly because of the existence of dark matter. The clustering of matter on extremely large scales became highly irregular, eventually forming a filament-like cosmic web made up of clustered galaxy groups and galaxy clusters. The vast empty regions enclosed by this cosmic web are what we call cosmic voids. In the past, astronomers generally believed that such extreme voids were far away from us. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie analyzed the spectral data of 35,000 galaxies and discovered a previously unobserved phenomenon. Within a radius of 1 billion light-years centered on the Milky Way, the density of galaxies was significantly lower than the normal cosmic level. Once beyond this boundary, the number of galaxies suddenly surged to 1.5 times the density inside it. They later named this hypothetical void the KBC void, using the initials of their surnames. There was also a fatal flaw in this research. Their method was very primitive. In essence, they were simply counting galaxies. But there is a large amount of interstellar dust in space, which can block the faint light emitted by many distant galaxies and make them impossible to observe. As a result, most of the academic community at the time believed that the Milky Way might not be inside a giant void at all, and that the apparent void was caused by observational error. The debate over whether we are located inside a giant void continued for more than a decade. It was not until the latest paper was published that research on this question achieved an important breakthrough. The new paper shows that this time, astronomers directly abandoned the old method of counting galaxies, and instead used baryon acoustic oscillations, method widely recognized in the field as more reliable. Baryon acoustic oscillations are large-scale structural traces left over from the early universe, and astronomers use them as a standard ruler for measuring cosmic distances. When the universe had just been born, all of space was like a hot, dense soup of plasma. Dense clumps of matter were pulled inward by gravity, while the pressure of high-energy photons inside them pushed outward. Between this inward pull and outward push, rings of spreading density waves formed in the early universe. These were sound waves. Later, as the universe slowly cooled, electrons and protons combined to form neutral atoms, allowing photons to travel freely. The sound waves that had been spreading were instantly frozen in place, and eventually became the fixed large-scale traces we see today in the distribution of galaxies. The intrinsic size of these traces is extremely stable, about 490 million light-years. That is why astronomers have long used them as a cosmic standard ruler, to measure the distances between galaxies. However, it is important to note that this ruler cannot be used directly. In the end, accurate distances still have to be calculated from galaxy redshift data. Redshift is especially vulnerable to systematic bias in a special environment like the KBC void. If the Milky Way really is located inside a giant cosmic void, then the redshifts we measure must contain systematic deviations. This is mainly because outside the void are high-density galaxy clusters and superclusters, where gravity is far stronger than inside the void. This strong external gravity constantly pulls galaxies inside the void outward, making their recessional velocities much faster than the velocity caused by the universe's normal expansion. As a result, their redshifts naturally become larger. In addition, according to general relativity, when photons travel from a strong gravitational field to a weak gravitational field, they lose energy. Their wavelengths become longer and gravitational redshift occurs. Inside the void, matter density is low and the gravitational field is weak. Outside it, galaxy clusters are dense and the gravitational field is strong. Therefore, light traveling from the edge of the void toward its center experiences an additional gravitational redshift pushing the measured value even higher. With these two effects added together, the redshift we measure from the center of the void must be higher than the true value. In other words, the expansion rate of the universe we measure may well have been amplified by the local environment we happen to occupy. This is why the KBC void offers a new way of thinking about one of the most difficult problems in modern cosmology, the Hubble constant crisis. One of the central problems in cosmology today is that different methods of measuring the expansion rate of the universe do not agree. Observations of nearby type Ia supernovae give a result of 73 kilometers per second per megaparsec. Observations of the cosmic microwave background from the early universe give a result of 67 kilometers per second per megaparsec. The two values differ by 6, which is already far beyond the range of systematic error in the two methods and cannot be explained by measurement error. To bridge this gap, astronomers have tried countless approaches, from modifying the laws of gravity to reconstructing the entire standard model of cosmology, but none has gained broad acceptance. The KBC void happens to offer a partial explanation for this difference. If we really are inside a void, then the redshifts of nearby galaxies would already be pushed higher than usual, meaning the nearby expansion rate we measure, not the true average expansion rate of the universe. Some studies show that after correcting for the bias, the local velocity field caused by the void environment, the Hubble constant values, obtained by the two methods can basically agree. But the mainstream academic view is that the effect of the KBC void alone cannot fully resolve the Hubble constant crisis and other physical mechanisms. Error still needed to explain the entire discrepancy. More importantly, the KBC void may even change how humanity understands dark energy. The concept of dark energy was proposed in the 1990s, after astronomers discovered that the universe is expanding at an accelerating rate. According to general relativity, visible matter alone cannot explain the accelerated expansion of the universe. So scientists inferred that there must be some unknown form of energy, spread throughout all of space, with negative pressure pushing the universe to expand faster. This is dark energy. According to the current mainstream model, dark energy accounts for 68% of the universe's total mass energy. The problem is that, to this day, we have never directly detected dark energy, and we do not even know what its physical nature is. The existence of the KBC void offers another possibility. Part of the accelerated expansion we observe may not be something happening across the entire universe at all, but a local effect measured from inside this void. Some studies suggest that this effect can ease many of the current observational tensions related to dark energy. However, the mainstream academic view at present is that the KBC void alone still cannot completely replace the dark energy model. What attracts cosmologists most about the KBC void? Not actually dark energy, but our location. According to current model calculations, the Milky Way is extremely close to the center of this supervoid, which creates a potential conflict with the first principle of modern cosmology. The Copernican principle is a cornerstone of modern physics, holds that Earth, the Sun, and the Milky Way do not occupy any special position in the universe, and that on large scales, the universe is homogeneous and isotropic, with no location being unique. Ever since Copernicus overturned the geocentric model, we have been dismantling our own special status. Earth is not the center of the solar system, the Sun is not the center of the Milky Way, and human beings are merely ordinary observers in the universe. All of our cosmological research is built on the Copernican principle, which is why the physical laws we observe from the Milky Way are assumed to apply to the entire universe. But if we happen to be located near the center of a 2 billion light-year supervoid, then things are different. It would mean that the cosmic observations we have made over the past several decades may all have been conducted from an atypical environment, and that the observational data we use to infer the laws of the entire universe have themselves been affected by local conditions. Of course, the vast majority of cosmologists today still believe that even if the KBC void truly exists, it is far from enough to overturn the Copernican principle or the cosmological principle. After all, cosmology itself allows for local inhomogeneities in space. But the KBC void does force us to reflect on the possibility that our understanding of the universe may be biased. In essence, the KBC void is still a hypothesis, but it is supported by reliable observational data and may even have a profound impact on the theoretical foundations of modern cosmology for humanity itself. However, this may be a good thing. In regions where galaxies are densely packed, high-energy events such as galaxy collisions, supernova explosions, and gamma-ray bursts occur frequently, making it difficult to provide life with billions of years of stable evolution. Perhaps, Instead, it was the relative emptiness of a cosmic void that gave Earth 4 billion years of stable external conditions, allowing us to evolve step by step from single-celled organisms into an intelligent civilization capable of raising its eyes to the sky and exploring the laws of the universe.